In this part of the lecture, we will look at how we can further optimize a HEN network design that was originally designed with the goal of maximum energy recovery and what are the degrees of freedom around that. Steam splitting is a technique used to optimize heat exchanger networks by allowing engineers to allocate heat transfer requirements efficiently among various heat exchangers and the process streams. Because the pinch analysis follow these heuristics of CP and the number of streams. So sometimes if these heuristics are not fulfilled, we cannot really have a good match between the hot streams and the cold streams. Okay, so stream split is a degree of freedom that can help us make the best use of heat source, that is the hot stream, and the cold streams. Okay, so for example, here you can see that above the pinch we need to satisfy the heuristics of CP. So let's say the CP rules are okay, but the number of stream rule is not satisfied here. So above the pinch, the number of hot streams should be less than or equal to the number of cold streams. And here you can clearly see that there are 3 hot streams while 2 cold streams, so we cannot have a feasible match between these hot streams and cold streams. Okay, so one way is to exercise our degree of freedom of splitting a stream. So we can split stream number 4 of stream number 5. Let's say we are splitting stream number 5, and we can split this stream in a way that the sum of the CP of these 2 streams is still equal to the CP of this stream number 5 here. Okay, but what value we assign of the value of CP we assign to these streams is still in our control, and that's the degree of freedom that we can use to have a perfect match between the hot streams and the cold streams. So we are still talking about the optimization of the network design. And here we see a design that's been developed using the pinch design method, and it is straightforward. Okay, and it respects the delta T min of that particular network design. Now, what we want to think about is that how we can actually optimize this design further. And once we start to optimize the design, we no longer care about the delta T min. Delta T min was something that we imposed when we were designing the synthesis of the network and when we are following the pinch design method. Now, all we want to do is to optimize the design for the minimum cost, and we don't care about the delta T min anymore. We just want to minimize the cost. So to minimize the cost of this HEN network, we are going to use the concept of utility loop or utility pathway that we also saw in the unit of process integration, but here we are going to discuss it in more detail. So here we have the same network again, but now with an important degree of freedom that is highlighted here, and this is a loop. Okay, so for a loop, what we do is that if we start at some point and we can follow a path, and that path actually end up at the same point where we start, and that's why we call it a loop. And a loop allows us to distribute heat duties between the exchanges in that loop. Okay, so for example, here we have this exchanger B, so we can reduce its duty by minus U, and if we are reducing it on this stream, we have to reduce it here as well by minus U, because that is actually one exchanger that is transferring heat between stream 2 and stream 1. And if we are reducing heat on this stream, then we have to increase heat on this exchanger because we need to keep the heat balanced for the final target temperature, that is 180. So we have to have a heat balance. Okay, so if we are reducing here by minus U, we have to increase on this exchanger by plus U, and if you are increasing here, then we have to increase the heat duty on this stream as well. Okay, so what we can see here that we have actually shifted some heat duty from this exchanger to this exchanger, and by doing that we actually change the size of this exchanger, but also the temperatures of the stream around these exchangers. So we start here at a temperature of 250, okay, and then we had because the duty was fixed, so we had certain temperature here at this point, okay, but now because the duty is reduced, so the amount of cooling that this exchanger can do is also reduced. It means that the temperature at this point would be higher than what it was originally when there was no shift in the heat duty. Okay, similarly for the cold stream, if you look at point E, so here you start at 20 degrees centigrade and you had a fixed duty, so you had some temperature here. But now with the increase in the duty of this exchanger, you are actually providing more heat, okay, and as such the new temperature at this point will be different from the old temperature when we didn't shift the heat duty, okay. So within a loop, although the energy consumption is fixed, but we can still shift the heat load from one exchanger to another exchanger, and by doing that we can change its area or the temperatures around it. So that is again a degree of freedom that we can use in order to reduce the cost of our heat exchanger area, okay. And this is because it is done after the energy heat energy recovery. So here our goal is mostly to reduce the cost, not the energy, because energy is already maximum energy we have recovered by designing this HEN, and now we are focused on the area reduction or the cost reduction. So here you can see the same network again, but with another loop that is highlighted here, okay. And again, what we are doing is that we are trying to shift our load from one exchanger to another exchanger while keeping the overall energy consumption of this loop the same. Okay. So again, if we start at this point A here and we reduce it by minus V. So to keep it balanced, we have to reduce it on this side as well. That is minus V. But now because we reduce the heat duty on stream 3 here, it created an imbalance on this stream, and as such we have to increase the heat duty of exchanger C by positive V, okay, because we have to keep the energy balance. So if it is reduced at A, then we have to increase at point C by V as well. And again, because if we are increasing it here, we have to increase it on this side, that is stream 4, because it's the same exchanger, and because we increase it this exchanger by V, it again created an imbalance on stream 4. So for exchanger D, we have to reduce it by minus V to correct for that imbalance. And because here we have reduced it by amount V, we have to reduce on this side of the exchanger by minus V. And again, that minus V will create an imbalance on stream 1, and then we have to increase it on point B by positive V, okay. And because we are increasing at this point now, we have to increase at this point, and you can see that by following this loop, we have shifted the duties, but the overall energy is balanced, because if we are increasing at one point, we have to if we are decreasing at one point, we have to increase it the point next to it, so that we can keep a balance, okay. So by shifting these duties, we have again changed the areas of these exchangers, and as such we have also changed the temperatures around it, as we discussed in the previous slide. But what is important is to see that by changing the heat duties, we have not changed the values of the hot and cold utilities. Okay, so the only thing that we are changing here is the area and the temperatures at the inlet and outlet of these exchanges, not the hot and cold utilities of the network. So here we use the same network again, but now concentrating on a different class of degrees of freedom. These are utility paths. So the utility paths are the paths or the connections from one utility going towards the other utility. Okay, so that is the shortest utility path that is represented here by this dashed line. Okay, So these utility paths allow us now to change the hot and the cold utility consumption while still maintaining the overall energy balance. So if we, let's say if we start from this point here, that is H, and if we increase the utility demand by W plus, or by increase by W, then we have created an imbalance on this stream 3, and the only way to correct that imbalance is to reduce the duty of this exchanger A by W. Okay, so if we are reducing the duty of exchanger A by W, we have to increase on this side as well, that is minus W, and by doing that we have created an imbalance of energy for stream 2, and the only way to correct for this imbalance is that if we increase the heat duty of this cold utility by W. Okay, so again, what we have done, we have increased the hot utility by W and the cold utility by W, while we have reduced the the duty of this exchanger A by W as well. Okay, so we have keep the energy balance. We have that will allow us to get the target temperatures. Okay, so we will still get our target temperatures because the overall energy is still balanced. But by shifting this load along this energy path, we have actually, in this case, we spend more on our hot and cold utilities, but now we need a much smaller exchanger A than before. Now, which option is the best is difficult to decide, because to find the best option, we have to change all these variables at the same time in a way to minimize the cost. Okay, so whichever network gives us the minimum cost in terms of the capital cost and the energy cost, that would be our choice for the HEN network. So to minimize the energy cost and the capital cost, we need to optimize the network. And this is a multi-variable optimization problem, actually quite complex, and we cannot solve it by hand, and we need a piece of software to find the solution in terms of the optimization variable, that is the cost of the system. So in the previous slides, we have looked at what is a utility loop, and we said that utility loop allows us to change the heat duties of the heat exchangers within a network without changing the energy consumption in terms of its utility and hot and cold utilities. While for the case of utility path, we saw that we can change the heat duty in a way that we can reduce the values of hot and cold utility. Okay, so now let's have a look at an example of how we can use the concept of utility path or utility loop to reduce the energy consumption of the network. So let's say that you have designed your HEN system, or you have an existing HEN system that you want to change or want to reduce its energy consumption. And for this network, for example, we have 1, 2, and 3 hot streams, and then we have stream 4 and 5, and they are the cold streams. And you have one heater and 2 coolers to provide the external utilities. And then you have make necessary matches following the usual heuristics of CP and the number of streams to have process to process heat transfer and to get the maximum energy recovery. So we want to see here that what we can do to optimize this network further in terms of energy minimization. And what it means that we want to reduce the external utilities, the hot utilities and the cold utilities, at the cost of increase in the area. Okay, so we can maybe afford to increase the area of some of these heat exchangers, and we want to reduce the external utilities. So in the previous slides, we talked about different degrees of freedoms that we can use in order to further reduce the energy consumption of this network, and we talked about stream splits, and for example here we don't have a stream split, but we do want to keep it in mind. Then we have loops and utility paths. But if we want to change the energy consumption or reduce the energy consumption of the network, loops are not useful to us because they fix the network energy consumption, and it is the paths that are more important to us. So given that we want to reduce the energy consumption of, for example, this heater, we might exploit a path that we have got here. Like, so let's have a look at this path, for example, going from this heater to this exchanger and then to this cooler here. Okay. So what we could do is that we can do minus X here, and then because we want to keep the heat balance on this stream, because we still want to get our targets, we have to do plus X here. And if we are doing plus X here, then we have to do plus here and then minus X here to keep this stream also balanced. Okay, so we have minus X, plus X, plus X, minus X. Okay, and the value of this X can be different depending on different delta T min that you want to try. Okay, for example, we can have 1 megawatt, 1 minus 1 megawatt, plus 1 megawatt, plus 1 megawatt, minus 1 megawatt. So we can move the energy along this utility path, and by doing that we actually reduce its heating utility and cooling utility by increasing the size of this exchanger here. So not only we have reduced the energy consumption, but we have also changed the conditions under which these exchanges are working on this utility path. For example, this exchanger here. Now the problem working with this utility path is that it only got a small energy consumption of that cooler here. Okay, only 1815. So the biggest reduction we can make on the energy consumption of this network using this utility path is of this cooler, and that will take us to 0 on that cooler. And once we have done that, then we have used up that degree of freedom completely. And what we then want to do is we want to reduce the energy consumption of this bigger cooler here. And to reduce the energy consumption, again, we need a utility path. And in fact, we have a utility path. So we have here, 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 then here, 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 and then finally connecting it this with this big cooler. So we could exploit that path to reduce the energy consumption. And in doing so, we can change the conditions throughout the network. And we probably need a larger number of changes to the equipment to give us some extra area. Now, if we are going to change the network structure, it might be interesting for us to use the insights that we have for the degree of freedom. And in order to reduce the energy consumption, we need to make a connection between this heater here and this large cooler here. And we have already a path in this network, but what we can also do is that we can make a new path to connect stream 1 with stream 5 and add an exchanger here, okay, between the hot stream and the cold stream 5. And by doing that, we have make a direct link between this heater here and this large cooler here, which was not existent previously. This network shows us a new heat exchanger here, and as such it allows us energy path going from H to here and here and here, and as such we can reduce the heat duty along this utility path. So here we have some reduction, plus here, and then minus here. Okay, so by placing this new heat exchanger between stream 1 and stream 5, we have reduced the hot and cold utility of this network. But not only that, we have to place this new heat exchanger, but also the existing exchangers like exchanger 1, 3, and 4, they would also need new areas, or they need to be recalculated in terms of their areas and the temperatures around them. So here we saw the nature of energy minimization of a network problem, and we can make structural changes, like for example, either we can use heat along a utility path, or we can introduce new exchanger that can create new utility paths to reduce the energy consumption of the network. Okay, so that is all for this part. At the end of this part, you also have a self quiz for you to try for this given network, and try to identify the number of utility paths, the number of loops, and based on that, how many number of degree of freedoms you have. Thank you for your time.